Note that I said in the previous example that the golf ball hitting the disembodied skull, which somehow still has the brain inside of it, was a typical example. No, that's not a typical example. I don't know that that's ever happened in the history of the universe, although golf seems to have arisen in Scotland, and the Scotch have certain customs in a somewhat violent past. I'm largely descended from Scots, so I'm not slamming anybody. I have a lot of affection for the Scots. So I don't know what my ancestors were up to in golf, but I doubt that it involved hitting disembodied skulls with golf balls. Anyhow, moment of inertia. The idea of moment of inertia is resistance to the effect of a net torque on angular acceleration. That's what I say here. What do I mean by that? Well, we know that it's torques that cause rotational accelerations. The greater the moment of inertia is, the more resistance we have to the effect of that net torque, in the sense that the less acceleration we're going to get for a given net torque. Okay? Greater the moment of inertia, the less acceleration we get from a net torque. Analogous to the way mass resists the accelerating effect of a net force. It doesn't resist it in the sense that it prevents acceleration, but there is less acceleration for a greater mass and a given net force. An example of moment of inertia, simplest example, is probably the hoop, where all the mass is concentrated at a radius of 1.5 centimeters. By radius, of course, I mean the distance from the center of rotation. We assume that the hoop is rotating about an axis through its center. If the hoop has a mass of 3 kilograms, the moment of inertia then is easily found. All the mass is at distance 1.5 meters, so we just take the total mass multiplied by the square of the 1.5 meters to get our 6.75 kilogram meters squared moment of inertia. And for a disk, okay, well, that's the moment of inertia for a hoop. Now, for a disk, if we have the same mass and radius, the moment of inertia that we get when we add up all the mr squareds, and you remember the approximate calculation we did for that, and then we saw how it went to an integral, and if you're in the calculus-based course, of course, you have to know how that works. We integrate the density times r squared between the center and the outside radius. In any case, the approximation that we got, or the integral that we do get, approximation was close to, and the integral was exactly equal to 1/2 mr squared, for m is the mass of the disk. And then if we calculate that for the given radius and mass, we get, well, exactly half of what we got before, 3.375 kilogram meters squared. Units are units of mr squared, which are kilograms times meters squared. Now we're going to abandon meanings for the time being and go on to some of the questions. We'll return to the meanings later. This is a strategy that I used in class because of the mix of the Physics 121 and 201 classes. Okay, our questions. First question is, in terms of what quantities do we understand uniform accelerated motion? Not talking about the quantities that we use to model uniformly accelerated motion or to do calculations, but the quantities we use to understand. And I think that those quantities might be average velocity, change in velocity, which is not the same as acceleration. If something changes velocity, it accelerates, but the acceleration is the rate at which velocity changes. Initial velocity, final velocity, displacement, and time interval. I think that we understand and reason things out in terms of these quantities. We formulate uniformly accelerated motion in terms of V naught, Vf, A, delta S, and delta T. And we've seen how that formulation works, since the average velocity is the average of the initial and final velocities for uniform acceleration, and only, well, not only, but for uniform acceleration. We have this relationship, and delta V is going to be the difference in velocities. And using these ideas and doing a little bit of algebra, we attain our 4 basic equations of kinematics, by which, given any 3 of these quantities, we can easily find the values of the other 2. Okay, how do we understand motion on a circle? In terms of what quantities do we understand motion on a circle? We understand motion on a circle in terms of what quantities? Well, theta of t, which is the angular position at time t, clock time t. Omega of t, which is the angular velocity at clock time t. And alpha of t, which is the angular acceleration at clock time t. Okay? And then we say that we could also understand it in terms of s of t, where s of t is understood to be the speed of the object, or the, I'm sorry, not the speed, the position of the object on the rim of the circle. In other words, how many meters has the object traveled by now around the rim of that circle, around the circle. The velocity of the object on the circle, which is of course a vector quantity perpendicular to the radial line. And the acceleration of the object on the circle. And there's another quantity, which might be the vector we'd call r of t, the vector from the center of the circle out to the position. Okay? And then we also understand in terms of centripetal acceleration, a equals v squared over r. Now, since v is r omega, as we know, then that's r omega squared, quantity squared over r, which is r omega squared. And we have the familiar relationships in terms of the definition of a radian. Our position in the circle is the radius times theta, velocity, radius times omega, acceleration, radius times alpha. And remember that theta is the number of radians. If we multiply by the radius, we get the distance by the definition of the radian. If we take radians per second and multiply by the radius, we get distance per second, and so on. So this is how we understand these relationships.